Alright, welcome back. So this is 11.5, the Binomial Theorem. We're going to use this as well as another concept to expand out a binomial expression being raised to a power. So the first way we're going to do is through what's called Pascal's triangle. So this is a pattern that we can use to determine the coefficients of the expanded a plus b to the nth power expression. Where the top row is just simply a 1 because anything raised to the 0 power is 1. Second row is 1 and 1 because anything to the first power is just the original thing, so a plus b, the coefficients are 1. And everything after that you'll find all on the outside rows are all 1s, and anything on the inside is going to be the sum of the two numbers that connected from the top row. So we would have 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, and then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. So if I want to do another row below that, a plus b to the 6th power, we'd have a 1, we'd have a 6 because 1 plus 5 is 6, a 15 for 5 plus 10, a 20 for 10 plus 10, a 15 for 10 plus 5, a 6, and then again a 1 at the end. So this is very useful to try to expand out an expression that's being raised to a not very high power, like, a 4th power, 5th power, that kind of stuff, where it'd be a little more annoying to FOIL it out, because like anything raised to the 3rd power wouldn't be that terrible to FOIL out. This would obviously be much quicker, but it's the kind of thing that really helps out for 4th, 5th, 6th powers kind of stuff. It's not really as useful when we start getting to powers beyond 6, because then we're starting to get into the numbers are getting much larger. We have to go through each row. If I want to find, for example, a plus b to the 10th power, I have to do the row for the 7th, 8th, 9th to be able to get to the 10th as well. So it becomes a little less useful as the thing gets too large, because then you reach a point where how much space you have to even write out the full triangle. And that's where binomial theorem comes into play, and that'll be what we'll be talking about at the second half of the video. So the way we're going to use this, we'll just use it for some basic ones, and then we're going to do this process to avoid the whole foiling out steps. So the way it's going to work is, so we have x minus 3 to the 4th power. So we know that for the 4th power, the row expansion is 1, 4, 6, 4, 1. The second number is always matching the exponents. And then so you just go it from there. So we know it's going to be a 1, and it's times x to the 4th power. It's only going to be the first term showing up. The second term is not there at all. And that's plus 4. Now that first term's exponent decreases, and the second term shows up as being raised to the, first power. And the combination of those two exponents should always add to be the overall exponent. So 3 plus 1 is 4. We're good. We then have a 6. X now becomes squared. Negative 3 is now squared. And then we have a 4 again. X is being raised to the first. Negative 3 is being cubed. And then finally, we're at the end. The first term disappears. All it is just simply the last term raised to the final power. So we evaluate each of those things. So this would just be x to the 4th. Negative 3 to the first is just negative 3 times the 4 is a negative 12. So it's negative 12x cubed. Negative 3 squared is 9 times 6 is going to be 54x squared. Negative 3 cubed is negative 27 times 4 is a negative 108. And then negative 3 to the 4th power is a positive 81. So this would be the fully expanded out version of x minus 3 to the 4th power, without having to resort to the use of foiling and most likely messing up somewhere along the way with the multiplication and combining like terms. All right, now both of them could have a coefficient. So just you have to make sure you're careful really each step of the way with your calculator and how these numbers are coming out, because they're going to start getting pretty large the moment we start having higher and higher exponents. So here we'll do a 4th power, pretty common one because it's not going to make it too large, but still get you to use the idea. So it's the first term being raised to the 4th power to begin with, a 1 in front, nothing to do with the second term yet. And then 4, that first term is now being cubed, the second term is now introduced to the first power. And then we go from there. So it's 6, 3x squared, 2y squared, and then 4, 3x to the first, 2y cubed, and then finally 1 with the 2y to the 4th. So when we get our full expanded answer, we're going to get 81 x to the 4th 216 x cubed y, 216 x squared y squared, 96 xy cubed, and 16y to the fourth. You notice here, because there was no subtraction term, all the terms stayed positive, whereas in the previous example, we were alternating positive and negatives because that second term is a negative. And again, negatives raised to odd powers yield negative results. All right, so just make sure you're careful with the calculator multiplying all that together, and then you should be fine with those coefficients. Now again, obviously this really works well for things to the fourth power, to the fifth power, and even the sixth power. But beyond that, it starts getting a little more tedious because you're creating each new level of Pascal's triangle to do that. So there has to be a better way. And this is also a shortcut. This is a pattern someone recognized, Pascal recognized. So there has to be a more mathematical process. And that's the binomial theorem. It's the mathematical process behind finding the coefficient of each term in the expansion. And that's where the combination comes into play. It turns out that the general kth term, so like, for example, if we're talking about the third term, k is 3, is this formula. nc of k minus 1 times a to the n minus k minus 1 times b to the k minus 1. Meaning, if I want to talk about, again, so let's say we're talking about, in this case right here, we have a plus b cubed. See how it's 3c 0? Because it's the first term, so k minus 1 is 0. A cubed b to the 0. 3c1, a squared b to the first. 3c2, a to the first b squared. And then 3c3, a to the 0, b cubed. You'll find that 3c0 is 1, 3c1 is 3, 3c2 is 3, 3c3 is 1. So it's applying the numbers you find in Pascal's triangle. And this works for no matter what. So we typically use this for things that are much larger. Fifth term of 2a plus 3b to the seventh power. So k is 5. And again, we know our n is 7. So our c is going to be 7, c, and then 4. It's always 1 minus k for that part. And then we have 2a and then 3b. Now, there are two exponents you need to combine to be 7. According to the formula, the 3b is the k minus 1, so that's going to be to the fourth power. And then 2a has got to be then the third power. Easy way you'll find it is going to be the numbers that go with the c, the 7c4. 7 minus 4 is 3. That's the first exponent. And then that second number, the 4, that's the second exponent. So you're pretty much just going to your calculator all in one step. The 7c4 times 2 cubed times 3 to the fourth. You obviously can't put the variables in there, but just going to be a cubed and b to the fourth. So 7c to the fourth times 2 cubed times 3 to the fourth is 22,680 to go with our a cubed b to the fourth. Now, if we had to do this full expansion, this would obviously also be just as tedious. We would have to do our 7c0, and then 7c1, 7c2, so on. We'd have a total of 8 of these things going on. So expand the full thing would be a very tedious process. So we're only going to do full expansion using Pascal's triangle with the exponents are going to be relatively low. I'll ask you to find individual terms when the exponents are much more massive, so you're not doing this massive problem for just one question. So here we'd find the third term of to the sixth power. So again, we could do this with Pascal's triangle. This is right on the edge of that. But again, we'll just find one term. So k is 3, n is 6. So we'd have 6c2, because again, that second number is always 1 less than k. And then the first number is always the difference of those two numbers for the exponent, so it's 5x to the fourth. And then it's negative 2y to, again, always 1 less than k, which is 2. And again, both those exponents add to 6, so we know we did it correctly. Putting it all into our calculator, we get 37,500 x to the fourth y squared. All right, so those weren't too bad of numbers. We certainly could find, the moment we start talking about things that are beyond that, so we start having something raised to the 13th power, 12th power kind of thing, you'll start finding your coefficients to be very, very massive, in the millions or even billions, and that's totally fine. All right, one last topic in Unit 11. We talk about functions with infinite series. This has some nice applications for what you're going to talk about in calculus. So let's get into that for next time.